Start by thanking the organizers, especially Olivia, who just showed up. Thank you for showing up. And yeah, thank you for putting together this great program. I understood maybe 20% of it so far. It's really so meaning the remaining 80 I'm learning a lot. I'm definitely intrigued about lots of things. So far the conference was heavily experimental, lots of beautiful talks about experiments and imaging, all sorts of beautiful imaging techniques. I have to apologize for taking you back now to things which are somewhat preliminary, maybe half-baked, but I think, at least for us, conceptually interesting enough that I hope to intrigue the experimentalists here, both on the spintronic side of things and on the imaging side of things. So we would definitely benefit moving these things forward, um, both using currents and spin transport, spintronic tools, as well as imaging, and hopefully it will become clear in my talk. I tweaked the title a little bit. Spin is really going to be playing a secondary role. The main topic is hydrodynamics, but it's going to be hydrodynamics of textures, not really a flow of some kind of conserved or approximately conserved spin. So spin will only enter the problem through magnetism, but it's really abstract hydrodynamics, and I'll formulate what I mean by that. I also snaked in elasticity to kind of pretend to be a bit closer to the core topic of this conference, and that sort of the next level by moving these hydrodynamic ideas to strongly correlated regimes such as Skermion crystal depicted here. So I'll explain what I mean by elasticity. Both hydrodynamics and elasticity will be abstract. Some fictitious abstract hydrodynamics and fictitious abstract elasticity. Mechanical system will be perfectly static and in the background, so I will not really induce or talk about the actual physical mechanics. Work was done primarily by my postdocs. Lots of ideas and the actual work was carried out, first starting with Sota Kei, who's moved on to become faculty at CUNY, and then these guys are still in my group, and it's all four incredibly bright set of people that allowed me to be part of these interesting developments. All right, the outline of my talk. Very rudimentary mathematics that I want to touch upon because it's so simple. I figure I will start with it. The topological aspects are different from the usual topological things you might have heard about recently. My topology is going to be topology in real space, and that will naturally give rise to the hydrodynamics. So in fact, every time you have topology in real space, that's the first point I'll try to make. It naturally leads you to think about hydrodynamics, and in spintronics, also on the imaging side of things, now we have tools to really look into these things. It's simplest to illustrate in 1D. Winding of some order parameter in 1D, that's the simplest illustration of topological phenomena in condensed matter, I think in general. Then I will talk about high dimensional generalizations. I will stop at 3D just because it's, for me, the largest physical dimension, but the generalization conceptually can go to any dimension. All right, so this will be like a little bit of a mathematical introduction of the concept. Then that's probably the main physics that I want to emphasize in this talk. Namely, I will tell you how we think this topological hydrodynamics can be experimentally probed by really asking what's happening at the boundaries, how we inject these topological textures at the boundaries, and how we're going to detect them. So that's really the core of this talk. And finally, this is like the special topics as part of this program that I will go through. Once we know how to inject and detect things, then we can consider different regimes, spin superfluids, Skermion crystals, and ultimately this the newest idea about thinking of dynamics and spin glasses also as a topological hydrodynamic phenomenon. All right. So this picture is enough to illustrate the basic principle. Consider a winding in the simplest example of what I'm after. Consider one-dimensional winding of some XY order parameter. It could be easy plane for a magnet, easy plane antiferromagnet, some other parameter that winds, okay, along some one-dimensional axis. So one-dimensional easy plane magnet. The total winding along this axis is a topological property of the texture. Okay, so I can, by smooth deformations, I can redistribute winding here and there, but the total winding is of course conserved, right? The density, I can also define the density. Winding is a local quantity, so I can define its density in this fashion as just the gradient of the phase that parameterizes the winding. So the integral of this quantity is conserved.
Yaroslav, sorry to stop you.
Oh, great. Okay.
So if I think of a magnetic material that's chiral, like one of these helical ones, but
Yeah.
not in this fermion state, can I then state that this helice is topological, or
Yeah. I mean, so far I'm not assuming. So this is mathematics. I'm not even assuming anything about energetics, physics, etc. I could have this winding in the ground state. I could induce this winding out of equilibrium. So I'll talk about physics later. But you're right. I mean, some helical system may already have such winding in the ground state. Then probably I will be more interested in additional winding relative to the ground state. But that will come later. And the key here is the easy plane character that allows me to define the winding. And that works only in one dimension, strictly speaking. Then in high dimensions, I may define some other type of topological property. So that's kind of the idea. Okay, so easy plane winding, that this quantity will be a conserved quantity. I can call it topological charge density or density of my topological quantity. So because the integral of it is conserved, I can start developing a hydrodynamic theory. So I can immediately write down continuity equation, and that's at that level is still mathematics, and then develop physics for what somehow the equations of motions in addition that I have to supplement to my continuity equation. Elasticity, other things will kind of naturally follow in appropriate, strongly correlated regime. What's that? An integer, yes. If depending on the boundary conditions. But yeah, if I fix let's say if I fix the angle to be 0 at both boundaries, then the conserved quantity will be integer. This will not play, so that's a very good point. It will not play such an important role for me. Namely, in the end, I will inject this quantity through the boundaries. So it will actually continuously go from 0 to 1 to 2, etc. But you're right, if I fix boundary conditions, then this quantity is conserved in multiples of integer. So I would only be able to change this quantity if I fix boundary conditions by an integer amount. But that's actually this talk comes from a different angle in which I'm going to be injecting things through the boundaries. Okay, so thank you for the question. All right, so I think that's kind of the main picture, and I'm going to be building on it. Now, again, just to connect to the ordinary hydrodynamics. In ordinary hydrodynamics, you have some particles moving around, and then the conservation law stems from just simple counting of those particles. In our case, we're counting certain twists in our texture, but in fact, we can also get to the regimes which are more like the particle-like hydrodynamics if these twists form solitons. And that naturally often happens if you have, for example, this easy plane, such an easy plane ferromagnet, and add I didn't say anything about the energetics, but let's now say there's some exchange interaction and the easy axis anisotropy along this axis, then such twists will naturally come in this domain wall kind of building blocks. And each of these domain walls that can now will have now a quantized charge of +1/2 or -1/2. That's, the sign depends on the correlate of this domain wall. Now will may act in certain regimes as a point-like object. And then, in fact, we can develop theory in terms of some kind of Brownian motion of these domain walls, or they could form a liquid, they could form a crystalline arrangement. So in the end, further down the road, my hydrodynamics, my elastics theory might actually become very much like the ordinary one in terms of the solitons. Okay, but it doesn't have to be. Okay, so the last slide about mathematics, also going to the high dimensions. And you can also ignore this slide if you want to, but it's simple enough that I thought that I might just mention it for completeness. So the winding, the topology associated with winding, mathematically we can think of it as topology that describes the mapping, is associated with the mapping from a real axis onto the circle. The circle, that's my order parameter space, which is parameterized by the angle. Okay, so my texture is a mapping from the real space to the circle, and such mappings are known to be topologically non-trivial. The winding number is what makes such mappings topologically non-trivial. Mathematically, you would say that the first homotopy group of the circle is 1, and this statement generalizes to mappings from any n-dimensional space to an n-dimensional circle. All right, and we'll see. I can now, guided by this, I can construct also the physical theories, kind of with this kind of natural hierarchy of generalizations from 2 to 3 dimensions, etc. So then you may ask, well, okay, what are the physical examples? Well, in 1D, like I said, it's a winding of some easy plane magnet. In 2D, it's a skyrmion texture. So we have the mapping from a plane now onto a 2-dimensional sphere, and the building block then of the topological texture is a skyrmion. And again, it can form a solitonic object stabilized by dipolar interactions, etc., Jarzynski-Maria interactions, etc. And this is kind of the coolest, newest example that we're still just kind of putting together. So these results are still kind of half-baked, preliminary, but we understand that the textures of spin glasses can be understood as a mapping from 3-dimensional space to 3-dimensional sphere, because spin glass, it's think of it as some random spin orientation that is locally rigid. So the texture, any kind of smooth perturbation, is parameterized by an SU2 order parameter. Yeah, and well, SU2 is equivalent topologically equivalent to a 3-sphere with opposite points being identified. So there's a representation of SU2 group that is equivalent to a 3-sphere. So essentially, at least for my purposes, well, with 2 opposite points being equivalent, but it doesn't really change the main topological properties. So the bottom line that we have also the 3-dimensional, sort of the natural 3-dimensional version of this story, which is maybe a little bit more difficult to visualize, but it's there. And okay, I'll talk about spin glasses at the very end, and we think one of the take-home messages also is that I think it's an interesting disordered magnetic materials that are locally somehow, at least locally have some rigid arrangement, could be very interesting also for spintronics. All right, but okay, just to proceed, at least to build up the intuition, I will focus primarily on these 2 examples which are easy to visualize. This 1-dimensional topological textures, just winding, and 2-dimensional topological textures, which are skyrmions. So this thing, this is 1-dimensional winding. This is like a wrapping of a plane that onto a sphere. So here I'm depicting a half of the winding corresponding physically to a domain wall. This is half of the skyrmion corresponding physically to a vortex, what some people call maron. Okay, so again, I think these are the objects which are familiar to people. So I think, and for my purposes, that's I think that's as much mathematical structure as I need for my story. All right, so let's now start building things up sort of towards physics. Like I said, just from the mathematics, from pure mathematics, the way we define the order parameter space, for free we get the continuity equation. Okay, and I emphasize that this continuity equation is not rooted in any kind of conservation law. Like namely, the conserved quantity that enters this continuity equation is not conserved because of some kind of symmetry sorry, no, I misspoke in the previous sentence. It's of course the conservation law, but this conservation law that does not stem from this symmetry. It's a conservation law that stems from the topology. Okay, namely, I have not assumed anything at all about the Hamiltonian. It's just the nature of the order parameter space that allows me to define this conservation law. And then later on, I can write down any kind of Hamiltonian, Lagrangian, and so long as my theory can be projected onto this order parameter space, I am good. On top of it, I'll have some parasitic effects, inevitably, that will bring me out of this low energy projection. So for example, for this XY winding, I will have phase slips, which will physically describe this order parameter coming out of plane and flipping over. So such parasitic processes will eventually lead to some relaxation and some deviation from such perfect continuity equation. But I can be definitely, equipped with this idea, I can definitely design a regime in which such processes are exponentially suppressed. So it can be really, really, really weak and negligible. Okay. All right. So, okay. And special cases, if you have a really perfect isotropic. Now, physically, if I assume, in addition to this structure, I assume a rotational symmetry around the axis out of the plane, so isotropic easy plane regime, that will lead to spin superfluidity. In addition to this topological structure, I have also conservation of spin along the z-axis. So then I can develop a dual formulation in which the conserved quantity will be actually this J rather than rho. I can in this for the spin superfluid, because the phase is conjugate to the spin density out of plane. It can be shown that this is actually proportional to the spin density. So then the continuity equation flips over for this guy being the conserved density. But that's a very, very special case. Yeah. No, it does not have to be. It can be static. It does not have to be. So I'll give you a concrete example later that it's really innately dynamic. Yeah, I'm interested really in the dynamic phenomena, out of equilibrium dynamic phenomena. All right, and then if you on top of this you add a strong, a weak anisotropy within this easy plane, then sort of smooth continuous winding underlying spin superfluidity, like I already said, will form this solid tonic semi-rigid or rigid objects with respect to which I can develop some kind of theory based on kind of Brownian motion of this object or crystalline arrangement and crystalline dynamics of these objects, etc. So the physics would be very different, but still somehow the starting point is this continuity equation. All right. If if you ask, well, how does this equations look like in 2D? Most of you have seen this equation. That's the skyrmion density. So the integrated skyrmion density, that's the number of skyrmions you have. That's the topological charts. Again, with fixed boundary conditions. Again, like the winding, it would be quantized in the integer. That's the density of the topological charge. Yeah. And like I said, it's conserved, and it's an object that I can define locally, whose density I can define locally. So that's a continuity equation, and I can actually explicitly write out again what the current is, and that's just what it is. Again, irrespective of what the Hamiltonian is, because like I said, the conservation law stems from topology, not from the actual physics. So these definitions, there's a purely geometric definitions that precede any Hamiltonian. And you could check that these two obey, again, the two-dimensional continuity equation. This is chosen to obey the continuity equation. Yeah, so let's say I start with this. So that's the logic. First, I have some texture in real space. I know that I have some topological invariant associated with the texture. Then I know that there is a current, and I just figure out what it is. And the same I can do for spin glass. And then, okay, that's a continuity equation. So that, again, this is mathematics, but that's kind of the general philosophy. Now the next step, the two next steps. Now I have to formulate the physics in the bulk. Okay, I still have to figure out like a theory for how to calculate rho and j, like Navier-Stokes equation. This continuity equation is always there, but then you have to develop something like Navier-Stokes equation that actually will describe the dynamics. That's one thing. Secondly, I have to develop theory of what happens at the boundaries, because I'm going to be using boundaries for injecting and detecting the hydrodynamics. That's kind of the main point of this talk. All right. And like I said, I will kind of build things up towards mechanics. So I will be asking, and I will develop in a special case when this topological texture forms solid tonic objects. I will develop some description in terms of mechanics. Maybe first starting with Brownian motion of this object, but then when they form arrangements, I can start asking questions about sort of rigid dynamics, distortions, etc., and the kind of physics associated with those dynamics. First, in the bulk, and I need to understand friction of these objects in the bulk, possible anomalous forces like Magnus forces. Again, these topological objects, they move not simply as particles. They might experience Magnus forces, etc. So that's something that needs to be understood in the bulk. And somehow, we're really interested and excited about these aspects, because I think this way we really connect to experiments and to spintronic tools for injecting and detecting these objects at the boundaries. And of course, there will be also some added dissipation at the boundaries. We can always ask about sort of rigid rotations of these objects, but in some special cases when there is isotropicity in spin space or approximate isotropicity in spin space, it will also be useful to ask about spin rotations, keeping the spatial structure fixed and then doing spin rotations. And like I said, ultimately in the crystalline arrangements, we can develop elastic theory in terms of distortions of this relative orientation of the solitonic crystals, solitonic lattices. All right, so let me go straight to the most interesting part. Is what happens at the boundaries, and let me start with the example of the one-dimensional winding textures. So before anything specific, writing down Hamiltonian and whatever, like let's just take a step back and try to intuitively think of how, if I give you an XY magnet, let's say, just to be specific, could be ferromagnet, whatever. How can you, and I want to, and let's say in equilibrium it's uniform. Now I want to inject the winding texture. How can you do it? So that's kind of actually a good question to the audience. Basically, you're all equipped with ideas that, in principle, would allow you to just immediately guess for how to inject such winding if you have some familiarity with spintronics. And the clue is by basically this analogy, this sort of geometric connection between the spin and and something like this, something. Well, that's a winding, right? Winding. What is winding? Winding has an orientation and has amount by which you wind, and geometrically, that's very much like spin. So that means if I have some ways to create some bunch of these spinning objects, well, we'll call it spin accumulation, and impinge it at the boundary of my XY system, that process might actually inject winding into the system. Geometrically, the structure of the winding and the spin are compatible, so you might expect that's what will happen, and generally that's exactly what's happening. That's a generic way to inject winding into any XY system without specifying the microscopic details of this XY order parameter. For example, it will work just the same in ferro antiferromagnet. Now, there could be no net magnetization, but just collinear XY ordering. All right. So when we know how to do it in spintronics, we can. Okay, let's say this is an insulator. I'm going to suppose throughout my talk that my magnetic system is an insulators, electrical insulators. So I can create spin accumulation only at the boundary of such an insulator, for example, by attaching a normal metal and sending electrical current in the vertical direction, tangential to the interface. That electrical current will generically, via the spin Hall effect, produce a spin accumulation out of plane at the boundary. And now the claim is that spin accumulation out of plane impinging on that boundary will always try to wind that order parameter at the boundary. Geometrically, they're compatible, and out of equilibrium, it will happen. Specifically, you can actually develop a theory for that, and we've done that a long time ago. I'm kind of just reinterpreting it in this language. You can, once you know what the spin accumulation is at the boundary, you can calculate spin current due to the spin accumulation impinging on this XY order. That spin current will be, it will be a component proportional to some parameters called spin mixing conductance of that interface and the spin accumulation. Spin current is, from the point of view of the magnet, is a torque by conservation of angular momentum. I'm going to suppose that at least at the boundary, the interactions are dominated by exchange, so the angular momentum is conserved, though that's not really essential. So that spin current is the torque from the point of view of this winding texture. Now, if I allow now for this angle phi to fluctuate at the boundary, for whatever reason, thermal quantum fluctuation, then that fluctuation will be associated with work. The work is just the torque times delta phi, and the torque is proportional to the spin accumulation pointing out of plane. Of course, if delta phi is rotating in plane, that the corresponding angular angle is out of plane. So that means that, let's say, for positive spin accumulation, you have positive work for clockwise rotation at the boundary and negative work for counterclockwise. Anything, many ways to do it. Spin hole is the simplest way. Yeah, it would be the simplest way. I could, of course, also build some kind of spin wave structure on the side. Yeah. Well, then it has to be. Well, then the spin accumulation will be polarized in plane. Will be in a, not quite in the right geometry. But in principle, you could somehow cook something up along those lines. Yeah, the spin hole is something that just immediately gives me, what I'm looking for in the simplest setup. Just put a metal on the side, pass a current, and that's it. And then just it happens. So, all right, then maybe the details will depend on the details of the Hamiltonian, the coupling, etc. But at least by this argument, you know that the winding will happen. Now it just remains the open questions are quantitative. And I'm not gonna, we have more. I can talk more about this, but let me leave it at that. I want to emphasize just the concepts for the purpose of this talk. All right, this can be generalized. You can actually, a few years ago, Hans, I should thank you for for this. Ideas. You asked a couple years ago at the conference on antiferromagnet if these ideas of spin mixing conductance can be generalized to a non-collinear antiferromagnet. So that's that basically led us to the ideas I'm going to tell you in the next couple of minutes. Now, I don't have to assume this magnetic arrangement to be collinear. Any non-collinear arrangement, so long as at least the relative arrangement is rigid, that will also be twisted by a spin accumulation. Okay, so if you apply spin accumulation to even some kind of non-collinear antiferromagnet or ferromagnet, that for the same argument, that spin accumulation will try to twist this rigid arrangement in a clockwise or anti-clockwise fashion with respect to the axis of the spin accumulation, and depending on the amount of the spin accumulation, right? You could develop theory for that in terms of, so the building block could be something that's related to what Rembert was calling rotational viscosity in some different context a couple days ago, the Rayleigh dissipation function. So that could be the starting point for constructing really kind of moving forward with the detailed theory. But I just wanted to say here that this coefficient, the G, that it's a generalization of the mixing conductance to this rigid rotation. So mixing conductance is a special case of this for the collinear arrangement. Now I have 3 parameters that parameterize this matrix. I have the 3 principal axes that I can define in terms of some scattering. The details of the scattering of this interface, so associated with this rigid rotation, there are 3 principal axes, and there are 3 sort of spin mixing conductances along those 3 principal axes, and they enter in the Rayleigh dissipation function that describes the coupling between the spin accumulation and this rigid rotation. So the point is that without mu, there is some dissipation associated with this rigid rotation that pumps energy into this metal, and mu in some sense shifts the energy flow of that dissipation. If mu is larger than h bar omega, then the work can overcome this dissipation, and that's just the spin torque, spin pumping physics, but in the more general setting.
Can you say
It's kind of like moment of inertia of some rigid body, right? Same sort of thing in a way. So if this rigid arrangement, it has some axial symmetry, then it's basically along those lines. All right, now like I said, following this blueprint, I can go to 2, 3, and higher dimensions. And now the idea is that mathematics gives me this topological hydrodynamics. For the physicists, what we have to figure out is really the kind of this physics at the interface. It's kind of generalization of this spin hole, spin mixing conductance physics. But in principle, we should be able to do it. It's possible to do it. Now you might ask, well, what happens in details, specifically in this two-dimensional case when the hydrodynamics is formulated in terms of the Skyrmion flows? It's even simpler than the spin hole effect. Turns out the simple adiabatic spin torque produced by electrical current flowing at the boundary, it exerts the work, again I just follow the same philosophy, the work that has a tendency to inject Skyrmion density into this material. Namely, if I allow for the arbitrary magnetic texture, now this is texture on a sphere, to fluctuate along this boundary, the work associated with this torque produced on that texture is proportional to the net Skyrmion flux through that boundary. So J is the electrical current that flows parallel. J sub S is the Skyrmion flux at the boundary that I defined earlier. Okay. In certain case of a rigid flow, yeah. But I'm not assuming, you don't have to make any assumption about rigidity. But if it was like a rigid object, if for some reason, it doesn't have to be rigid at the boundary, but if it was and entered the system, yeah, it would be just the Skyrmion density times the velocity. Yeah, but it doesn't have to be rigid. Okay, it could be anything. And yeah, if you look at what's happening as a function of time, along the boundary, so the boundary is parameterized, let's say, as a y-axis as a function of time, then the work per unit length, per unit time is proportional to the Skyrmion density in the space-time, in 1 + 1 dimensional space-time along the boundary. So again, the integrated work is just proportional to the Skyrmion number that you inject. So in this paper we kind of formulated this theory for the injection of Skyrmion. We developed more like detailed theory in the limit of Brownian motion of Skyrmions, assuming that there's some Dzieloshensky-Marie interaction that stabilizes the Skyrmion texture into the solitonic objects, and then you can, making some assumptions about specifics of what's really happening in this film, we can develop a quantitative theory. And the first prediction that we suggested, experimental thing to look for, would be inject the Skyrmion density by passing current at one end, and then at the other end reading out voltage, sort of as a drag, as a non-local drag effect, a non-local conductance, transconductance. And that voltage, by the reciprocal effect, if this current injects, does work proportional to the Skyrmion injection, you can show that the Skyrmions which come out at this interface will produce electromotive force that again is exactly proportional to the flux of the Skyrmions coming out, irrespective of the details of how those Skyrmions come out. So you could develop a very nice quantitative sort of theory for the in terms of Brownian motion of the Skyrmions, and in terms of some thermally assisted injection of them at the boundary. The next step forward, and that's the elasticity, is to basically consider various regimes of the Skyrmions when you go towards crystallization and transition. So if you start forming, for example, a Skyrmion crystal, so the function of magnetic field in the Dzieloshensky-Marie interaction, you could go between some collinear order Skyrmion crystal and the helical order. So this is something that experimentally is well established. There are magnetic films that have this kind of phase transition. So we propose now the transport techniques to look at the signatures, or transport tools to look at the signatures of such phase diagrams of how magnetic textures are forming. Of course, starting this magnetic phase transitions through this, through the Skyrmionic crystallization, etc., using transport is great. If you can do imaging at the same time, it would be terrific. Like Patrick was talking about imaging. Enviscent imaging of vortices in superconductors. By the same token, we can also do imaging of these structures. Then you for sure would know that this kind of non-local transport signature is from the physics that you think it is. Let's see if okay, okay. I didn't have an. I don't have a slide about it, but the reciprocal of this torque is electromotive force. If you calculate electromotive force associated with texture dynamics at this other end, kind of sort of is the same kind of mathematics at the same level. The electromotive force is proportional to the flux of this current coming out at the other end. So it's just reciprocal to this torque. And finally, like I said, because this notion of going back to this twisting example, the notion generalizes to an arbitrary, even non-collinear texture. We can apply this idea to a spin glass, and it would be kind of cool because now the randomness in the system completely washes out any kind of anisotropy. So we can now we don't have to worry that the spin accumulation is appropriately aligned with anisotropy of your system. Applying the spin accumulation to a spin glass at any orientation will just start twisting this rigid order in the plane perpendicular to your spin accumulation. So this emergent spin superfluid is totally isotropic, and we call it SU2 superfluid. It's something that might play a role in a recent experiment, might not. I just wanted to again just make this connection for the experimentalists to be aware of. A report of some non-local transport signature in a disordered amorphous YIG, which at least kind of conceptually consistent with this story, but probably or more likely to be not the case because this material conducts also. So a better material would definitely be necessary to pin it down. But yeah, I think the experimentalists should look for non-local transport signals mediated by spin glasses. All right, let me skip through those two slides and finish with the take-home messages. Thank you. The energy is not. That you mean the exchange energy? Right. Oh, in the limit of Heisenberg ferromagnet. Let's say. Yeah. But you can generally ask. Well, there's some energy, right? Constant energy. Yeah. 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 So let's say in this simplest. Okay, there are two extreme cases. We can start already in the regime in which you have Skerman lattice. So that means because of Jolshinsky-Marie interaction or whatever, it means that if you had the uniform, you kind of implying, let's say, creating Skerman on top of some uniform background. So in some cases, the Skermions actually have negative energy. So then they form crystals typically. So you could already be in the regime in which you already have Skermions there. No, well, in some, let's say Jolshinsky-Marie interaction is the simplest way to do it. In practice, again, these bubble materials could be dipole-dipole interaction. So anyways, the bottom line, the Skermions could already be there. And then this becomes a problem of, okay, I didn't get into the detail of elasticity. So with this current, you're basically creating a pressure on the Skermion crystal. The Skermion crystal starts sliding along. So that's kind of an elastic regime of Skermion dynamics. Then what you really just, with this current, with this physics, you're exerting directly pressure on the Skermion crystal, and then kind of flows at an angle because of Magnus force. So it's a lot of interesting physics because it's a gyrotropic crystal because of the Magnus force associated with the Skermion motion. But if you go back to this system, the Skermions, so namely it's an energy cost for a single Skermion, then the Skermions would be thermally activated. So then this energy cost should not be much higher than kBt, should be around the ballpark of kBt or so. Otherwise, the signal will be exponentially small. No, it's stabilized by Jolshinsky-Marie interaction. Maybe Andre and another theorist too. Just a quick question. No, I am not talking about spin superfluidity. It says spin superfluidity is a certain idealized case. I mean, the whole point here that we go beyond that idealized case. Not that I have anything against spin superfluidity, but that's another topic.